Alright, so the final problem on the exam asks you to help a student figure out the expression of the flow rate in integral form on the onset of flow of a Bingham plastic in a rectangular channel parallel plate flow chamber. I gave you this diagram to help you visualize that a little maybe easier to put your coordinate system right down the center of your channel, and the total height is h. So when you look at this problem, you got to know a couple of things in there. One is you're working with a Bingham plastic, and you want to try to figure out what happens at the onset of flow. And again, I give things that the flow is induced by a pressure gradient, the channel is horizontal, and the flow is steady and fully developed once it begins to flow. So first thing when I do these kind of problems, the Bingham plastic flow through a rectangular channel, I'm going to think of, okay, what do I know of a Bingham plastic? Well, we know these two situations, that whenever the shear stress is less than the yield stress, your velocity gradient is going to be equal to 0. That doesn't mean the velocity is equal to 0. It just means that your velocity is constant in this region. And then whenever the shear stress is greater than your yield stress, your shear is dictated by this equation right here. So we have flow through a rectangular channel. So again, your shear stress in a rectangular channel is given by this equation. I would have expected this to be on your equation sheet. You can derive it. We've done this exercise in the homework a couple of different times. So you can go straight to this equation knowing that we have the simplified case of a rectangular channel flow. So now that you have your shear stress in this rectangular for a rectangular channel, you can plug this shear stress into this equation right here, and you see I have plus or minus for this generalized equation, and down here I have negative. So this yield stress is going to be negative when your shear stress is negative, so these are going to have the same sign. So what you can do now is you can solve for the velocity profile. So what I'm doing now is just rearranging the equation so that I have it in terms of the velocity gradient, and now I'm going to integrate both sides to get the velocity profile. So here's our velocity profile, and in terms of our unknown C1 that we've got to solve. So how are we going to solve for C1? Well, what I'm looking for is at the onset of flow. We know that the onset of flow is occurring first near the walls, because at these points near the wall, that's going to be our highest shear stress. So the shear stress is the greatest at the walls, because at that point you have the greatest velocity gradient, right? It's going to be this is going to be incredibly high because it goes from 0 at the wall to some number right beside the wall. So that's going to give you a really large velocity gradient, and therefore a really high shear stress. So let's look at these portions really close to the wall. So at y is equal to h over 2, we know that our velocity is going to be equal to 0 due to no slip. So we plug that into the equation that we just showed you to solve for C1. We solve for C1 and we get this, and then we plug that into our equation. I can go ahead and rearrange that equation, and you get this velocity profile. Again, you see something really interesting is that the velocity profile, the first term right here, is the velocity in a rectangular channel for a Newtonian fluid right here, this part, and then this other part over here is due to it being a Bingham plastic, and it has a yield stress tau naught. So this is our shear stress, this is our velocity expression right here for the onset of flow, what's happening really close to the wall. So again, it's at this point that we say is going to be called between y0 and h over 2. So this point right here is going to be y0, or this, and this other point on the other side could be negative y0. And you're going to have this is where the yield stress is overtaken by the shear stress of the fluid, and it's going to cause the onset of flow. Now between 0 and delta y is going to be right in this area right here on this side, and down in this area on this side we're looking at. At these 2 points, now at y naught right here and at negative y naught, this equation and this equation have to equal one another because of symmetry. So we could just take this equation right here and plug in y naught into y, and this is the equation that I've labeled Vx2 is what's going to describe the point between 0 and y naught, and it'll also describe, because due to symmetry, 0 to negative y naught. So, and as you can see, that this is just a constant. Vx2 is not dependent upon y, and so it's constant because of the fact that dvx over dy is equal to 0, because your shear stress, remember, is less than your yield stress at this point. So therefore, in this problem, you know, I'll draw it a little bit bigger. You're going to have some point right here where you're going to have like a kind of a part of a parabola. It's going to be a blunted flow, and then you're going to have your other part of the parabola where this is going to be negative y naught, and this is going to be y naught, and this is what your velocity velocity profile is going to look like. Okay, so we need to figure out what the total flow rate is through here. So if we just want to look at the top half of it, you're going to have one section right here that you can describe by one equation, and that's going to be Vx1, and then you have this other section down here which is Vx2. So we have this part that we need to describe in our flow rate, as well as this part, and then multiply all that times 2 because of symmetry. You got this other side of the pipe you need to worry about. So again, our flow rate is given by this expression, and as I said before, we need to multiply it times 2, or we need to integrate it in terms of our z direction. So we go from 0 to w, which is our width, so that's coming out of the paper right here. The width of our channel is from 0 to w, and now we need to, like I said before, we need to integrate from 0 to y naught for this middle portion right here, and we plug in Vx of 2, this equation, which again is all a constant, and then we do the part that's really close to the wall between y naught and h over 2 in this given, and this is going to be integrated with Vx1 at this equation. So this is our integral expression that is describing the flow rate of the Bingham plastic through the rectangular channel on the onset of flow. And the sketch that I've given here is the sketch of the velocity profile that we're looking for in the problem.